So in this video, we're going to continue our discussion of probability distributions. So previously, I did a whole video series on the binomial distribution. So in this video, we're going to take the next step and talk about the Poisson distribution. And let me just point out, that's how it's pronounced, the Poisson distribution. It's not, like someone said in a class once, the Poisson distribution. That did happen, I promise. It's the Poisson distribution. So it's very similar to the binomial distribution, and actually it's kind of a cousin of the binomial distribution. So if you do know something about the binomial distribution, this will make a whole lot of sense because it works in a very similar manner. Now it's most often used not only in statistics in certain situations, but also in fields like operations management, specifically what's called queuing theory. In a queue, especially if you're in Britain, a queue is what we call in the United States waiting in line. So you're in the queue or you're in line. And if you think about that, let's say you go to a bank and you walk into the bank and you get in line. Then once you're in line, you wait a certain amount of time and then you proceed forward to have whatever banking services you need. There's a service time, and then when you're done with your service, then you walk out. Well, that whole process is called queuing theory in operations management and management science. So this is used not only in stats, but in other disciplines with very practical implications. And actually the example we're going to use in this video is a very simplified version of a queuing theory problem, or sort of a waiting in line problem. So all that being said, let's go ahead and dive right in. So this is what I call the checkout line example. So there are some people there waiting in the checkout line at the grocery store, and here's our problem. Let's say that you are a cashier at Walmart. It's 4:30 p.m. and your shift ends at 5 o'clock. Now the store policy is to close your checkout line 15 minutes before your shift ends. So in this case, your checkout line should end at 4:45. That way you can finish checking out whatever customers remain, and of course you'll take your register probably to the office to balance out and things like that. So it's 4:30, you're scheduled to get off your shift at 5, but they're going to close your checkout line at 4:45 to make sure you get out on time. Now, by examining the overhead cameras, like the security cameras in the store data indicates that between 4:30 and 4:45 p.m. on each weekday, we're going to assume this is a weekday, an average of 10 customers enter any given checkout line. So you can imagine, as a customer, you're walking around the store and you get all the things you need, and then you kind of walk up to where the checkout lines are and you decide, probably by which is the shortest, which line to get in. So once you become part of that line or part of that queue, that's what we're considering here. So between 4:30 and 4:45 each weekday, on average, 10 people basically get in line. And that's all we're worried about. We're not worried about how long it takes to check them out or anything like that. Just the number of people that get in line. So here are two questions we're going to use in this video. What is the probability that exactly 7 customers enter your line between 4:30 and 4:45? Another question we're going to answer, what is the probability that more than 10 people arrive into your line between 4:30 and 4:45? Now remember, on average, or we're expecting 10 customers to come into our line during that 15-minute period. But we're going to look at the probability for exactly 7, and then the probability for more than 10, which is more than we would expect. And of course, that means you probably would not get to work on time. So here's our time frame. Between 4:30 p.m. and we're going to say 4:49:59. I'm not going to include the exact 4:45, but it's really not important. Now here's the question I want you to answer with your intuition. Which outcome, so the number of customers that get in line, is your expected value? Or sort of the mean number that come? And actually you should already know this, it was in the question. So we have a continuum here, and we could have 0 customers during that 15-minute period. It's probably not that likely, but it could happen. Theoretically, we could have an infinite number of customers come into our line. Now, is that actually going to happen? No. But that's why it says in theory. That's part of the Poisson distribution, is it could theoretically go all the way to an infinite number of customers, but of course that's not going to happen. Now, what number of customers would you expect? Well, it's not a trick question, because remember, in our problem it said we would expect 10 people to get in line. That's what the store figured the average was. So that is our expected value. That is our mean value. And in these type of problems, the expected value, remember, the expected value is just the mean of a discrete probability distribution. So expected value and mu, the symbol mu there, the mean, are really the same thing in these type of problems. So don't get confused, they mean the same thing. But again, we would expect 10 customers in that 15-minute period. Now, if we graph that in Excel, and I'm going to do that in a different video to show you how I got this graph, you will see that on the left-hand side, we have 0 customers coming into our line. That's the x-axis along the bottom. That's the number of customers. Along the y-axis, the vertical axis, is the probability associated with each outcome. So you can see that down at the left-hand side, we have the probability of 0 customers. Well, that's not that likely. As you can see, the bar is very, 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 very short. It's very small. There is probability there, but it's not very much. And of course, as we go up the number of customers, the probability gets higher and higher and higher. So if you look at 10, which is the dark green bar there, remember that was our mean. We can see that the probability there seems to be about 0.125, somewhere in there. But also, the probability for 9 customers is the exact same. And sometimes that happens in these discrete probability distributions. So remember, this is for our time interval of 4:30 to 4:45. Now, even though 9 customers and 10 customers have equal probabilities, the mean or expected value is still 10. It just means that the probability of 9 or 10 customers arriving is the same. It doesn't affect the mean in any way. And that's just what sometimes happens in discrete probability distributions. But just remember, the height of each bar is the probability for that outcome. Now, as you can tell, as we go past 10 and then on to 11, 12, 13, 14, number of customers, the probability keeps going down again. Again, in theory, this goes all the way out to infinity. It's kind of a limit problem. So if you've done other mathematics, you kind of understand what limits are, but it never really, gets anywhere. It theoretically goes to infinity, and the probabilities become so small that they are basically 0. Okay, so you can see that this distribution is very similar looking to binomial distributions, and that's not really by accident, because they are related. They're not the same, but they are related. So, let's talk about a formal definition here. The Poisson distribution. What it does is it focuses on the number of discrete events or occurrences over a specified interval or continuum. That could be time, length, distance, or whatever. It's over some continuum. And the number of events that happen only within that interval. And that's what makes the Poisson what it is. Number of events in a specified interval. And we have a new symbol for that. It's called lambda. So in the Poisson, we have a new symbol that at least we haven't used in my videos. So it kind of looks like a, I don't know, a little triangle thing. But it's the Greek letter lambda. And that is just the number of occurrences over the specified time interval. And again, this is what, you can get symbols mixed up, but lambda is the same thing as the expected value, or the mean. These all kind of mean the same thing. You could actually substitute them in, and actually I'll show you that in a minute, and it doesn't change the meaning. They are the same thing. So let's look at our checkout line example. Lambda in that case is that we have 10 customers per 15 minutes. So our lambda here is 10. Now it's important to point out there that's not a fraction you're going to simplify. I mean, you could, but it would change. It would be like 2 customers every, 3 minutes or something like that. But we're talking about a 15-minute interval. That is the interval we decided on. And 10 customers are expected during that 15 minutes. So our lambda here is 10. So do not try to simplify that because we're interested in our 15-minute period. So let's talk about a few characteristics more formally. Just keep in mind that the Poisson is discrete outcomes. So 0, 1, 2, 3, 4, etc. The number of occurrences in each interval can range from 0 all the way to, theoretically, infinity. It describes the distribution of infrequent, rare events. Each event is independent of the other events. Describes discrete events over an interval, which we already talked about. That's kind of what makes it what it is. And the expected number of occurrences are assumed to be constant throughout the experiment. So this is something we kind of assume. So think about our example. During a 15-minute period, we expect 10 customers. So we kind of assume that those 10 customers arrive to our line evenly. Now, is that actually going to be the case in real life? Probably not. Now, there are types of queuing problems that you can have a constant arrival rate, or a constant service rate. And as far as a constant service rate, I'll give you an example right now. And that is the automatic car wash. So when you drive your car into a car wash, at least here in the United States, your car moves along that car wash at a constant speed. And every car goes through it at the same speed. So in that case, the service of the car wash is constant no matter what car goes through. But in our checkout line, people are going to arrive sort of at different times. But for this interval, as long as we're dealing with this interval, it really doesn't matter. We're kind of assuming that everyone arrives at even times. So just keep that in mind. It's not really that important, but it is just a characteristic of the Poisson distribution. So, of course, there's a formula that goes along with it. And here's what it looks like. Now, that's kind of crazy looking, but I don't want you to freak out. It's actually fairly simple. So here we have the probability of an outcome, X. So we could say 7 customers, 12 customers, and that would what X would be. That equals lambda raised to that X power multiplied by E, which is a constant. Okay, we'll talk about that in a minute. Raised to the negative lambda power divided by the factorial of X. Or it can also look like this. In some books, you'll see it this way, where instead of lambda, they use mu. But remember what I told you a couple of slides ago. They're the same thing. Okay? Now, more formally, lambda is the formally correct way, but I have seen it with mu in place of lambda, but it doesn't change the meaning. It's the same thing. So X could be 1, 0, 1, 2, 3, 4, all up to infinity. That's the number of occurrences we are interested in. So in our problem, the first question, we're interested in 7. So x would be 7 in this formula. Lambda or mu is the long-run average, which is the same thing as saying as the number of occurrences we have in whatever interval we specify. And then E is the constant. Remember, if you haven't had this since high school or whenever, it's that 2.1718 number, which is the base of natural logarithms. So it's that button on your calculator that says E. Okay, it's just a constant. So all we have to do is plug in or substitute our numbers into this formula to find our probability. So let's solve our first one. What's the probability of exactly 7 customers? So here is our formula. I'm going to use the lambda version. So what is the probability of exactly 7 customers that enter your line between 4:30 and 4:45? So x here is 7. Lambda is 10, because remember we're expecting 10. That's our average, our long-run average. And then E is a constant. It's always E. So 2.1718. Now we substitute those numbers into our formula here. So lambda is 10 and x is 7. So 10 to the 7th multiplied by e to the negative 10, because it's e to the negative lambda, divided by 7 factorial. And that's because 7 is our x. Now when we do that in our calculators, we come up with 0.09, which of course is 9%. So the probability that exactly 7 customers come to our line between 4:30 and 4:45 is 9%, or 0.09. Now if we go back to our graph here, we have at the top there we have lambda equals 10 and x equals 7. That's what we're interested in. So if we go over to the 7 bar in our graph, I've covered that in green so you can see it. If we go over to our axis, look where it meets up at 0.09. So we can use our graph to check our calculation. And they both concur, so we know it's correct. The probability of 7 customers coming into our line in that 15-minute interval is 0.09, or 9%. Now there's a way to figure this out in a TI-83 calculator. That's what I use. I have a TI-83 Plus, but I'm sure this is the same for all the TI models. So here's our graph, and again we're interested in the height, or the probability, which is the same thing, of that green bar, which is x equals 7. Now the function in the calculator is the Poisson PDF function, and it requires 2 arguments, our lambda and the number of occurrences we are interested in. So to find that, you just press the second and the vars button. That takes you to the distribution menu. You'll scroll down and you will find the Poisson PDF function. Press enter. Then you type 10,7, which will put the command into your calculator. So it'll say Poisson PDF 10,7, and then of course press enter. That will give us the exact probability of x equals 7, and it comes back 0.09. So you can find this exact probability in the TI-83 or TI-84, I'm sure 85 and 89 calculators. Now a couple of things to keep in mind if you do this on your calculator. Number one, it's very easy to accidentally select the binomial PDF function, because they're basically right next to each other. So always make sure you're selecting the Poisson PDF when you're finding an exact probability. Now on that note, this command in the calculator is for finding the probability of an exact outcome. So exactly 7 or exactly 12 or exactly 4 or whatever else. We're going to talk about the Poisson CDF function here in a minute. So PDF is the specific probability of any specific outcome. Okay, now remember the second part of our question. What is the probability of more than 10 customers arriving. Well, if we look at this, anything more than 10, what would include 11, 12, 13, 14, 15, so on. So we're interested in the green part of our graph here. But how do we find that? Well, if you remember, in the binomial videos, I did something very similar. So remember that the entire probability distribution has to add up to 1. That's just sort of the law of probability distributions like this. So if we want to find the green, what we can do is we can take 1, which is the whole, and then subtract or sort of chop off the purple, and that will leave us with the green. So we can sort of do a puzzle here and figure out the green by subtracting the purple part from 1. So how do we do that? So here's our graph. So what's the probability that more than 10 customers enter your line between 4:30 and 4:45? So here's our formula again. Now x is 10. Now why is that? Why is our outcome of interest 10? Well, if you look on our graph, that is the upper limit of the purple region we're going to want to subtract out. So we're going to find the purple area and subtract it from 1. So x, in this case, is 10. Lambda is always 10 for this distribution. And then, when I said lambda is always 10 for distributions of this problem. So it can obviously be different for different problems. So e is a constant 2.1718. So now we can go ahead and do this. So to find the green part, we take 1 minus the probability all the way up from 0 to 10. And I'll show you how to do that here in a second. So we go ahead and subtract that purple part out. And we have 1 minus 0.583 equals 0.417. And that is the probability of the green part of our graph. Now I do want to point something out here, which I'll show you in the next slide. Remember to find the cumulative probability there in the purple. In our calculator, we will not use the Poisson PDF function. We're going to use the Poisson CDF. But I'll show you that in the next slide. So here's what we're trying to find. And the function we want in this case is the Poisson CDF. And the C in that case stands for cumulative. So the cumulative will give us the probability all the way from 0 all the way up to 10. So 1 minus that will give us the green part. So just remember the PDF version of the function gives us an exact probability at any given exact outcome. The CDF gives us the cumulative all the way from 0 up to whatever number we specify, in this case 10. So we go ahead and do that subtraction out, and the whole area of the green is 0.417, which means the probability of more than 10 people arriving into our checkout line between 4:30 and 4:45 is 41.7%. That's a pretty good probability, or a pretty good percentage, as far as more than 10 people coming into our line during that time. So our answer summary. What is the probability that exactly 7 customers enter your line between 4:30 and 4:45? Well, it was 0.09, which is 9%. What is the probability that more than 10 people arrive? Well, that was 0.417, or 41.7%. So again, these are just the probabilities of these specific outcomes given the time interval we're interested in and the number of people we expect, the mean number of people we expect to come into our line based on some previous data we have or calculated. So finally, a bonus question. Let's say your manager decides to be nice And you get to close your register at 4:40 instead of 4:45. How many customers do you expect to arrive between 4:30 and 4:40? So here is our change we got to do. We expected 10 customers in that 15-minute interval. What if we change it to a 10-minute interval? Now that 10 minutes is within that 15, okay? So it's not outside that 15, but the 10 minutes within that 15-minute interval. What would we expect? Well, actually, it's a simple cross-multiply ratio problem, and that is 6.67 customers. So, if we close our register at 4:40, during the 10 minutes from 4:30 to 4:40, we would expect between 6 and 7 customers, somewhere in there, to come into our line. So if we change the interval, we have to change our expectation of customers. But again, that 10-minute interval is within our original 15-minute interval, and that's very important. So what if we do a graph of this distribution? Well, it looks like this. The time interval is now 4:30 to 4:40, and our expected is 6.67. So we can use Excel to do this graph, and if you look, the most probable outcome is 6 customers. And the probability of that is over 0.15 or so, 0.155, something around there. And you can see on either side of that, the probability gets lower. So the probability of 5 is a little bit lower than 6, the probability of 7 is a little bit lower than 6, and it falls off from there and looks a very similar shape as our previous one. Okay, just a quick review and we are done. Remember, the Poisson can have discrete outcomes, 0, 1, 2, 3, etc. The number of occurrences in each interval can range from 0 to, theoretically, infinity. It describes the distribution of infrequent or rare events. Each event is independent of the other event. It describes discrete events over an interval. So an interval of time, distance, etc., and that's important. That's sort of what makes a Poisson what it is. And finally, the expected number of occurrences are assumed to be constant throughout the experiment. And that's important because of the past question I did in the bonus section. So I changed the interval from 15 minutes to 10 minutes. So 10 minutes within the original 15-minute interval. Because I assumed the arrivals into the line were constant, I could do a simple ratio. So again, in real life, it doesn't always work that way, but it's a good enough approximation that we can go ahead and make that assumption. Okay, so that is our introduction to the Poisson distribution. Now, I'll be doing some more videos on this, some more examples, some more real-life applications. So make sure you check back for those if you're just watching this for the first time. Just a few things to keep in mind. If you're watching this because you are struggling in a class, I want you to stay positive and keep your chin up. If you're on here trying to improve yourself in your education, that's what really matters. Okay, the fact that you're making the effort to learn and understand and better yourself, that is what really matters, at least to me, and I hope it does to you. Please feel free to follow me here on YouTube and or on Twitter. That way when I upload a video, you know about it. If you like the video, give it a thumbs up. It does encourage me and other screencasters to keep making our videos. On the flip side, if you think there is something that I can do better, leave a comment below, and I will try to incorporate that in the future videos. And finally, as you learn, I want you to have fun. I want you to enjoy learning, knowing that in the future,